You think you understand magnets? Opposite poles attract, like poles repel. Simple, intuitive. Everyone knows this. But here's what they don't tell you. There is no magnetic force. Not in the way you think. Magnets don't attract or repel because of some fundamental magnetic interaction. The force you feel when you push two magnets together, that resistance, that pull, is not what it seems. It's not magnetism, it's quantum mechanics. It's the Pauli exclusion principle. It's relativity. It's electron spin. And when you understand what's really happening, when you see the actual mechanism behind magnetic attraction, you realize that magnets are one of the strangest, most quantum, most relativistic phenomena in everyday life. I'm Leonard Susskind, and I've spent 50 years thinking about quantum field theory and electromagnetism. And I'm going to tell you what magnets really are. Not the simple story, the actual physics. And it's far stranger than anyone told you. Let me start with what everyone thinks they know. Magnets have north and south poles. Opposite poles attract. Like poles repel. This has been known for thousands of years. The ancient Chinese used lodestones, naturally magnetic rocks, for navigation. In the 13th century, Petrus Peregrinus mapped the field around a spherical magnet and identified poles. In 1600, William Gilbert published the Magnete, showing Earth itself is a giant magnet. But knowing that magnets attract and repel doesn't explain why. For centuries, people had no idea what caused magnetism. It was a fundamental force, like gravity, just something that exists. Magnets attract because that's what magnets do. But this is not an explanation. And the truth, discovered in the 20th century through quantum mechanics and relativity, is far more subtle. The force you feel between magnets is not a fundamental force. It's an emergent phenomenon, a consequence of quantum mechanics, relativity, and electron interactions. Let me show you why. First, let's talk about what magnetic fields actually are. In the 19th century, James Clerk Maxwell unified electricity and magnetism into electromagnetism. He showed that electric and magnetic fields are two aspects of the same thing. The electromagnetic field, moving electric charges create magnetic fields, changing magnetic fields create electric fields. They're intimately connected. Maxwell's equations describe how they evolve and interact. This was revolutionary. It showed magnetism is not separate from electricity. They're manifestations of a single electromagnetic force. But this still doesn't explain permanent magnets. A bar magnet sitting on your desk isn't moving. There's no obvious current. Yet it creates a magnetic field. Where does that field come from? The answer is electrons. Specifically, electron spin. Every electron has an intrinsic angular momentum called spin. It's not that the electron is literally spinning. Spin is a quantum property with no classical analog, but it behaves like angular momentum. And crucially, spin creates a magnetic moment. The electron acts like a tiny magnet. In atoms, electrons orbit the nucleus, and they also have spin. Both the orbital motion and the spin contribute to the atom's magnetic moment. In most materials, these magnetic moments are randomly oriented. They cancel out. No net magnetism. But in ferromagnetic materials like iron, cobalt, and nickel, something special happens. The electron spins a line. Many spins point in the same direction. Their magnetic moments add up. The material becomes magnetized. This alignment is what creates a permanent magnet. Now, here's the key question. Why do the spins align? What makes them point the same direction? This is where quantum mechanics comes in. The alignment is caused by the exchange interaction, and the exchange interaction is pure quantum mechanics. Let me explain. In quantum mechanics, electrons are indistinguishable. If you have two electrons, you can't label them. You can't say this one is electron A and that one is electron B. They're identical particles. And for identical fermions like electrons, the wave function must be antisymmetric under particle exchange. If you swap the two electrons, the wave function changes sign. This is a consequence of the Pauli exclusion principle. The Pauli exclusion principle says no two fermions can occupy the same quantum state. This has profound consequences. It's why atoms have structure, why electrons fill shells, why chemistry works, and it's also why ferromagnetism exists. Here's how. The wave function for two electrons can be factored into a spatial part and a spin part. The total wave function must be antisymmetric. So if the spatial part is symmetric, the spin part must be antisymmetric. And if the spatial part is antisymmetric, the spin part must be symmetric. Now, symmetric spatial wave functions mean the electrons are closer together on average. Antisymmetric spatial wave functions mean they're farther apart, and the energy depends on this. Electromagnetic repulsion between electrons is minimized when they're farther apart. So antisymmetric spatial wave functions have lower electrostatic energy, but antisymmetric spatial requires symmetric spin. Symmetric spin means the spins are aligned, both pointing up or both pointing down. So the configuration with aligned spins has lower energy because it allows the electrons to avoid each other spatially. This is the exchange interaction. It's not a new force. It's a consequence of quantum statistics and electromagnetic repulsion. The Pauli exclusion principle forces electrons with aligned spins to stay apart. This reduces electrostatic repulsion. The energy is lower, so in ferromagnetic materials, it's energetically favorable for spins to align. Many electrons align their spins. The material magnetizes. This is why magnets exist, not because of a magnetic force between spins, but because quantum mechanics and electrostatics favor spin alignment. Now let's talk about magnetic domains. Even in a ferromagnetic material, not all the spins are aligned throughout the entire material. The material divides into domains. Within each domain, spins are aligned. But different domains point in different directions. Why? Because a uniformly magnetized material creates a strong external magnetic field. And magnetic fields store energy. The field energy is proportional to the volume of space with non-zero field. So large external fields cost energy. The material can reduce this energy by dividing into domains. If half the domains point up and half point down, the external field cancels. No field outside. Lower energy. When you magnetize a material, say by placing it in a strong external field, you're forcing the domains to align. The domains with spins parallel to the field grow. The others shrink. Eventually, most of the material is a single domain. The material is magnetized. Remove the external field and the domains might stay aligned. If the energy barrier to flipping is high, this is a permanent magnet. Or the domains might randomize if thermal energy is sufficient to overcome the barrier. This is a temporary magnet. Now let's get to the force. When you bring two magnets together, what force are you actually feeling? The obvious answer is that magnetic fields from one magnet interact with the magnetic moments in the other magnet. And this is true, but what is that interaction physically? The magnetic field from the first magnet exerts a force on the moving charges in the second magnet. But wait, in a permanent magnet, there are no moving charges. The electrons are in atoms. They're not flowing. How does the magnetic field exert force? The answer is that magnetic fields exert forces on moving charges and on magnetic dipoles. An electron with spin is a magnetic dipole. The magnetic field exerts a torque on the dipole, trying to align it with the field. And if the field is non-uniform, there's also a force pushing the dipole toward regions of stronger field if the dipole is aligned with the field, or away if it's anti-aligned. So the magnetic force between magnets is the force exerted by the field of one magnet on the magnetic dipoles in the other magnet. These dipoles are electron spins. The field exerts force on the spins. The spins are in atoms. The atoms are in the solid. The force is transmitted through the material. You feel it as the push or pull between magnets. But here's the deep point. The electron spin is not a little magnet in the classical sense. Spin is a purely quantum property. It has no classical analog, yet it creates a magnetic moment. And that magnetic moment interacts with magnetic fields. This is quantum mechanics manifesting at macroscopic scales. The force you feel between magnets is quantum mechanical. It's the result of quantum spin, quantum statistics, and the Pauli exclusion principle. Now let me tell you about relativity. Magnetism is also a relativistic effect. This sounds crazy. Relativity is about speeds close to the speed of light. Magnets move slowly or not at all. How is relativity involved? The answer is subtle. Magnetic fields are the relativistic consequence of electric fields. Let me explain. Imagine a current-carrying wire. The wire is neutral. It has equal numbers of positive charges in the nuclei and negative charges from electrons. The nuclei are stationary. The electrons drift slowly, creating the current. In the wire's rest frame, there's no net charge. The wire is neutral. Now imagine you're an observer moving parallel to the wire at the same speed as the drifting electrons. In your frame, the electrons are stationary. The nuclei are moving. Because of length contraction from special relativity, moving charges are closer together than stationary charges. In your frame, the spacing between nuclei is contracted. The spacing between electrons is not. So in your frame, the wire has a net charge. What looked like a neutral current in one frame looks like a charged wire in another frame. And a charged wire creates an electric field. This electric field is what appears as a magnetic field in the original frame. Magnetism is the electric force seen from a different reference frame. This is the relativistic origin of magnetism. Magnetic fields exist because of relativity. They're the electric field transformed by changing reference frames. This was known even before Einstein. Maxwell's equations automatically contain relativity. Einstein recognized this and used it to develop special relativity. So the magnetic force between magnets is fundamentally an electric force modified by relativity and quantum mechanics. It's not a separate force. It's electricity plus relativity plus quantum mechanics. This is why magnetic forces are much weaker than electric forces. The magnetic force between two magnets is much smaller than the electric force between two charged objects with similar charge density. Magnetic forces are suppressed by factors of v squared over c squared, where v is the typical velocity of charges and c is the speed of light. For electrons and atoms, v over c is about 1 over 137, the fine structure constant. So magnetic forces are about 10,000 times weaker than electric forces. Yet we notice magnets because magnetic forces can act over larger distances and don't cancel out easily like electric forces do in neutral matter. Now let me talk about diamagnetism and paramagnetism. Not all materials are ferromagnetic. Most materials are either diamagnetic or paramagnetic. Paramagnetic materials are weakly attracted to magnets. They have unpaired electrons with net spin. In an external magnetic field, the spins partially align with the field. The material becomes weakly magnetized. Remove the field, and thermal motion randomizes the spins. No permanent magnetization. Paramagnets are weakly attracted to magnets. Diamagnetic materials are weakly repelled by magnets. This is more subtle. All materials have some diamagnetism. When you place a material in a magnetic field, the field induces currents in the electron orbitals. These induced currents create a magnetic field opposing the applied field. This is Lenz's law. The induced field opposes the change. The result is a weak repulsion. All materials have this effect. But in most materials, it's overwhelmed by paramagnetism or ferromagnetism if present. But in materials with no unpaired spins, diamagnetism dominates. Water is diamagnetic. You can levitate a frog in a strong enough magnetic field because the water in the frog's body is repelled by the field. This was done at Radboud University. The frog was fine. Superconductors show perfect diamagnetism, the Meissner effect. When a material becomes superconducting, it expels all magnetic fields from its interior. The induced currents are strong enough to completely cancel the applied field. A magnet placed above a superconductor levitates. This is quantum mechanics at a macroscopic scale. The superconducting state is a quantum state involving Cooper pairs of electrons. The expulsion of the magnetic field is a quantum phenomenon. It's one of the most direct demonstrations that quantum mechanics operates at everyday scales. Now let me address a common misconception. People think ferromagnetism requires unpaired spins, that only atoms with unpaired electrons can form magnets. This is mostly true, but not always. Some materials with paired spins can still be magnetic due to subtle quantum effects. But the main point is that ferromagnetism requires not just unpaired spins, but also the right crystal structure and interactions to allow exchange coupling. Iron, cobalt, and nickel have the right combination. Most elements do not. Even among ferromagnetic materials, the properties depend sensitively on temperature. Above a critical temperature called the Curie temperature, thermal energy overcomes the exchange interaction. The spins randomize, the material loses its ferromagnetism. For iron, the Curie temperature is 770 degrees Celsius. Heat iron above this, and it stops being magnetic. Cool it back down, and magnetism returns. This shows that ferromagnetism is a delicate balance between quantum mechanical alignment and thermal disorder. Quantum mechanics favors alignment, thermal energy favors randomness. At low temperatures, quantum wins. At high temperatures, thermal wins. Let me end with what magnets teach us about quantum mechanics. Magnets are everyday objects. You can buy them at a store, stick them on your refrigerator. They seem classical, mundane. But the force you feel is deeply quantum. It's electron spin. It's the Pauli exclusion principle. It's exchange interactions. It's quantum statistics. None of these have classical analogs. They're purely quantum, and they manifest at macroscopic scales. The force between two magnets is one of the most accessible demonstrations that quantum mechanics is not just microscopic, it affects the everyday world. Your refrigerator magnets are quantum mechanical devices. The fact that you can feel magnetic force is proof that quantum mechanics is real and operates at human scales. And the force is also relativistic. Magnetism exists because of special relativity. The electric force in one frame becomes magnetic force in another frame. So when you hold two magnets and feel them push or pull, you're experiencing relativity. You're experiencing quantum mechanics. You're experiencing one of the deepest aspects of physics through a simple, everyday phenomenon. After 50 years of studying physics, I still find magnets remarkable. They seem so simple. North pole, south pole, attract, repel. But beneath that simplicity is an intricate dance of quantum spins, exchange interactions, relativistic transformations, and electromagnetic fields. The force between magnets is not fundamental, it's emergent. It arises from quantum mechanics and relativity, and that emergence is beautiful. It shows how complexity arises from simple underlying rules. Magnets are quantum, magnets are relativistic, and magnets are proof that the universe is stranger than it appears. Thank you for watching. Now you know what the hidden force behind magnets really is. Welcome to quantum electromagnetism.